Living Room Logic.
Season 2 is supported by FameLab Ireland.
Everyone, it's Season 2! Woo! We are back! Me and Andrew, Living Room Logic, at it again.
Can you believe we got here again?
No, I can't at all.
No, me neither.
But, you know, a lot has changed since our first season. We've learned so much and we've had an amazing time making our first season. Yeah. So we thought, for the start of the second season, we might as well come flying in with a bang, right?
Yeah, why not? Maybe a big bang of sorts.
A big bang, maybe the big bang. The start of the universe?
What a great segue we made off the cuff. That's brilliant stuff.
We're just born professionals now. This week we want to talk to you about the start of the universe and what we're all made of and what everything is made of, and maybe then jump very quickly to how it all ends, and we'll talk about some crazy ideas for the end of time.
And some unfounded opinions as well. So,
absolutely.
We'll have a great time.
So before we actually get into the theory that is the Big Bang Theory, Andrew is going to talk us through how we kind of came to this theory and what the ideas of the start of the universe were before that, or was there a start?
So like the big question, right, and it's literally a question as old as time, is, has the universe always been, or did it have a beginning? Mm-hmm. You know, that's always been the question that people were kind of asking before we had any of these theories. And there were a lot of different trains of thought. Like Aristotle believed that the universe always was. There wasn't a beginning. And that idea was called the steady state hypothesis, right? They were saying that it's steady. The universe always existed. There's no end, no beginning, la-di-da. Mm-hmm. But that was challenged by the early Jewish philosophers and Islamic philosophers, because that challenged the beliefs of Abraham, you know, of the creation of the universe by a greater being. Okay. So that's kind of like, it's actually in religion. Religion and those philosophers were the first people to kind of go, I don't think the universe always was. I think there was a beginning. Mm-hmm. So that kind of developed, and not so shockingly, it was a priest who first came up with the idea, or the first theory that kind of pointed towards maybe something like the Big Bang. Mm-hmm. He was out there looking at the stars, and he was noticing that things kept moving apart, this lad, Father Georges Lemaitre. Mm-hmm. And he didn't understand why. And he was like, right, what happens? Everything in the universe is moving apart. The stars are spreading out from each other. Distant galaxies are spreading out from each other. Everywhere he looked very far away, everything was spreading out and leaving and going away. Weird. So he was like, okay, well, what is everything going away from? Is there like some scary Karen in the center of the universe that everyone's like running away from and trying to avoid, you know? Like, is there something pushing everything apart? So he was like, okay, I'm going to track them all back. What's the origin of all of this? You know, in the same way that if you saw someone throw a ball, you could kind of look at the speed and direction of it and go, right, I know which way it came from. I can maybe model it going back in time and see, you know, who threw it or something like that. And he published a paper, and the paper had a very, very smoncy name, okay? His paper was called The Homogeneous Universe of Constant Mass and Growing Radius, accounting for the radial velocity of extragalactic nebulae.
I don't know, for a priest, that's very scientific.
There was a lot of major scientists who were priests, and that's an interesting thing to actually have a discussion about another day. You have to remember, back then, they were searching for creation. That's what they were looking for. Like, that was so cool. That was the debate. The people of religion were actually saying, no, we need to prove that there is a creation moment. But anyway, this Father Lemaitre, he came out with this theory, right? But it was in French, right? He wrote it all in French. Mm-hmm. And since not many people read French work, it didn't become famous immediately. 2 years later, Edwin Hubble, whose name you might recognize from that big-ass telescope, came out and was like, hey, I have an idea. Yeah, like he didn't steal the idea. He just came up with it on his own 2 years later.
On another occasion.
It was interesting, though, this finding, because if you remember back at the... we had the quantum mechanics and particle physics episode in the first season. That's a not so subtle plug. Go check out season 1. It wasn't that bad.
No, not subtle at all. And
no. But in that, Einstein had an opinion. He was unhappy with someone else's finding, and then he was proven wrong. And again, that happened here, because Einstein came out after reading this paper, and he said to Lemaitre, he was like, your calculations are perfect, but your physics is crap. That's what he was saying. He was like, the math is good, but the physics is crap. Wow. And he was really not happy with it. And eventually they ended up together at a few conferences around MIT, right, in like the 30s and 40s. And they actually had like a one-on-one explanation meeting where Lemaitre just explained it to Einstein in maths. Einstein at the end of it stood up and applauded, and he was like, what Lemaitre then did was he actually integrated Einstein's theories of relativity to say, like, this is where it all comes from. Mm-hmm. And he put it together.
There are two people that have really might not even like each other, or might really not see eye to eye, and then they go in a room and they bang heads, and then they're like, that's actually great.
yeah, exactly.
This is like, an amazing idea.
Yeah. And after that, it became really well accepted. And they were like, oh my God, the universe is expanding. Everything is going away. So if we track it backwards, we can find the origin of the universe. And this is what Lemaitre then published in a book. And it was called the Primeval Atom Hypothesis, right? Of this, like, if you track everything back, it all comes from one super dense location with all of the energy and mass in the universe, right? He also called this the cosmic egg, which I think is just, a great turn of phrase.
That's great. Like
the cosmic egg.
The cosmic chicken pooped out. Like what?
Maybe the cosmic chicken that pooped out the egg was God. Who knows? They pulled it all back, right? So now they had this idea. What if all of the universe was compacted into one small, primeval little ball? Unimaginable. This doesn't make sense. And it didn't make sense.
Yeah.
The idea, right, was that, okay, we need a way to prove this. Because when they tried to model it, it didn't make sense. Physics was broken. If you try to pull everything in that tight, it's broken. It doesn't make any sense anymore.
Yeah.
So, they were like, right, the start of the universe would have been outrageously active. It produced an outrageous amount of radiation. And if we look, we should still be able to find somewhere some of that cosmic radiation, right? Mm-hmm. And it's a good story, right? There were these two scientists working in California, right? They were working in a different kind of telescope that detected radio waves. And they were getting this weird signal. And they were kind of going out, and they were like, God, did a pigeon come and take a poo on our telescope again, messing up our data? And they were going out, cleaning the bird poop off of the telescope and trying to,
blame the birds for,
Oh, they were blaming the birds because it didn't make sense. But then they kept looking at it and they were like, what is this? Because it's constant. They had found a spot in space that they could look far enough back and actually pick up on the cosmic background, which is a leftover from the Big Bang. Because what happens is, during the Big Bang, all of this energy and all of these waves were flying around the place with so much energy. Mm-hmm. But that was 13 billion years ago. Mm-hmm. And since that time, all of that energy has not vanished. Rather, it's slower. So these high energy waves have slowed down, and now they're around the same wavelength as a radio wave.
Yeah, that's so cool.
And that's actually why you get static on your old-timey TV. If if you had that in your day,
Yeah, or your radio. I mean, car radios.
Yeah, exactly. If you turn on the wrong address on your AM or FM radio, you're going to hear loads of static, and that's the cosmic background. That's your proof of the Big Bang, because that can only really come from a Big Bang.
Mm-hmm.
They proved it, and they won the Nobel Prize in the 70s for proving it. And
crazy.
Yeah, and the priest Father Lemaitre, who discovered this, he lived long enough to find out that it was proven.
That's amazing.
So they can track it all back. The Big Bang is a theory. It's a thing. It happened.
Mm-hmm.
And I suppose the next thing for us to go into is what exactly happened.
From a great cosmic chicken pooping out a cosmic egg,
the
to
ethereal chicken.
That cosmic egg turning into this 13.8 billion year old stretched out light. As Andrew said, the Big Bang Theory, it's our most accepted theory for how the universe started. And there are a couple other theories, but by far the amount of actual evidence going back to something like a trillionth of a second after the Big Bang, we actually have evidence for it, which is quite incredible. During this cosmic egg phase, or what is also known as a singularity, all of our laws of physics kind of break down. But if you could imagine it, all of the universe, all of matter, it is such a small point that you could imagine that it would be so hot and so dense. So before we go any further, I must just give a very brief overview of what those kind of laws of physics are. Not to coarsely plug, but actually very relevantly plug the quantum episode and particle physics. We basically talk about these 4 different fundamental forces, okay? It sounds like Star Wars, but there are 4 fundamental forces of nature, okay?
Made in a universe long, long ago.
Yeah. In a galaxy far, far away.
Yeah.
You don't need to know too much about them. But one of them's gravity. Another one is electromagnetic stuff. Stuff that runs your electricity and magnets, and that's all linked. And then stuff at really small atomic scales, okay? Called the weak and strong nuclear forces, and that's what binds things together at the kind of really small scale. There's another thing as well that we need to say. It's called scientific notation. It's a really quick and easy way of talking about huge or tiny numbers, okay?
Yeah.
And it's going to make sense for the next couple things, because the numbers here are so small or super large, okay? So, for example, in terms of time for seconds, 10 to the power minus 2 seconds is just 2 zeros behind a 1. So 0.01 seconds. Okay? The other way around, 10 to the power of plus 2 is just 10 by 10, which is 100. 1 with 2 zeros in front. Okay? Very quick, very easy. Now, this is where it gets very cool and very small. Just after the Big Bang, at 10 to the minus 36 seconds. 36 zeros.
Are you sure you don't want to read that out?
Oh, yeah, no, sure. Let's do it. Let's do it. No. But I actually looked up the size of this number, and it's actually called 1 undecillionth of a second.
Undecillionth. I like that. I like that.
The temperature of the universe cooled to 1 octillion degrees, which is 10 to the 28.
Wow.
1 with 28 zeros in front. So that's a huge temperature. Tiny, 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 tiny scale.
Yeah.
But it was actually just before this that those 4 fundamental forces that I talked about were 1. And our laws of physics broke down at that scale. Okay?
I guess.
But after that time, which is such a small number after 0, after that moment where the cosmic egg kind of popped, those fundamental forces started forming. And this kick-started an important thing called a phase transition in the universe. And this saying, phase transition, is so important here, okay? Because several of these things happen in the first second of the Big Bang. And a perfect analogy for a phase transition is when you freeze water. Water is a liquid at room temperature. And then 0 degrees Celsius, it becomes a solid, ice. Other way around, if you have liquid water at room temperature and you bring it up to 100 degrees Celsius, it boils. It changes its phase. Okay?
Okay, yeah, I'm with you.
So here's the thing. This phase transition and the unlocking of the physical forces that we know, those 4 physical forces, released an insane amount of energy, and at an octillionth of a second, which is 10 to the minus 28 seconds, unbelievable, but just a tiny little bit later, the universe started expanding exponentially. That means that it expands at an incredible rate. It wasn't before and now it is. Faster than the speed of light. From the size of a single atom to about the size of a football.
Oh.
Okay?
Yeah.
Now, that doesn't sound too big, but actually, this is the same kind of relatively as a grain of sand growing into a space rock that spans 10 light years.
Right.
So it's relatively, and we're going to use that word a lot, but relatively it is a humongous change.
And for anyone who was missing something there, a light year is a distance. How far light can travel in 1 year worth of time, which is huge. Light can travel from the sun to the earth in 8 minutes. So imagine that speed going on for an entire year to imagine how big this is. And then how big was from a grain of sand to how many light years?
10.
10. It's unimaginable.
Yeah, so it actually, you would think, based on Einstein's laws of general relativity, nothing can travel faster than the speed of light.
Yeah.
Unless they're not traveling through space.
Mm-hmm.
But it's actually space itself expanding.
Yes.
It's not expanding into anything. Or at least we don't know what it's expanding into. Weirdly enough, this doesn't violate Einstein's theory of relativity, which is amazing. It blows my mind. Like, it's so crazy.
I had the same thought when I was reading about this, because I was like, because I read that and they were like, actually no, Einstein's like speed of light limit is things traveling in space. Space can do whatever it wants. And I was like, what does that even mean?
Yeah, no, what the hell does this even mean?
Yeah. I was like, that doesn't make sense.
Take this in. Meanwhile, as all of this stuff is happening, the universe is still the size of a football. And it's still only gone to, 10 to the minus 28 seconds. That's incredible. And how do physicists know that? You know, that just shows you the power of theoretical physics. It's absolutely incredible.
Yeah.
So let's keep going. So from then, that second step to the universe is a football, okay?
Yes.
And it's expanded faster than the speed of light. From then until about a tenth of a trillionth of a second, so that's 10 to the minus 13 seconds, elementary particles begin to form as a quark gluon plasma. And we talk about quarks and gluons in that previous episode we were talking about in season 1. And these particles and their antiparticle pairs, they become continuously created and destroyed in collisions because there's just too much energy for them to kind of stay stable.
Yeah.
But because of quantum fluctuations, a fraction more matter was created than antimatter. And that's the single reason why matter exists today.
If it was equal, it would have been nothing.
If it was equal, all of the gluons that were made, they would have decimated each other. And so, yes, you would have still had a universe, but you wouldn't have had what we call normal matter, which we are made of.
If everything was spreading from one point, you'd think it'd be even in all directions.
Well, the funny thing is that we actually find out that at the grandest scale that it is homogeneous or smooth or whatever you want to call it. But these tiny little changes at the tiniest scale mean that there was a 1/billionth the amount of particles that survived. That's what happened at 10 to the minus 13 seconds. By about a second, right, after time zero, the universe is expanding at a much slower and steadier pace.
Yeah.
And quarks and gluons begin to bond to form protons and neutrons. And they have a collision shootout with their antiparticles. And 1 in a billion of those also survive. So this is another kind of phase transition. And it's another massive shootout of particles. It's amazing that this is all of this has only happened in a single second.
Yeah.
And then this happens again for electrons and positrons a little later. But by this time, the observable universe is about 20 light years across, and matter as we know it has formed, okay?
Yeah.
Think of the amount of stuff that just happened in a single second.
I know.
20 light years in a single second.
It's nuts.
Unbelievable. Scrounge break! Do you suffer from erectile dysfunction? Well, you're in luck. Go to patreon.com/livingroomlogic and donate a few quid a month to the podcast so you don't have to think about that sexy stuff. And get a few exclusive rewards from your favourite nerds.
As the universe grew and grew, there more and more space. Like all of this time, the universe is expanding, it's getting bigger. All of this heat and all of this radiation and all of this plasma and all these kind of particles forming, the universe begins to cool down, right? And as it cools down, so right, you start dropping the temperature, all of these subatomic particles can start coming together to form atomic particles. You know, you're talking about your neutrons and your protons. It can start forming the most basic of elements. You're talking hydrogen and helium. At that first stage where you have all of these different particles in the universe, first a lot of hydrogen, and then it cooled down, and any particles that haven't gotten a date yet, they could turn into hydrogen or they could turn into helium. As it got cooler and cooler and cooler, it could develop heavier and heavier things. Because if it was too hot, it would melt down, break apart. Heavier elements like plutonium and iron and things like that. The majority of the elements in the universe is hydrogen. Most of the elements in stars are hydrogen and helium. Why? Because those were the initial elements that could be formed by the particles in the universe. So they had the most time to form.
That was that matter that was created.
But you know what happened after all of that? Once all of these stray subatomic particles found their mate for life or until fission and found each other and chilled out, there was an age of darkness because the energy had dissipated. Balance was restored. It took so much time for anything to happen after that, because now you're talking about the first elements had to bring themselves together by gravity.
After those key atomic elements were made, there was a pause. But it is interesting, and there's one really cool thing to say, that at about 400,000 years after the Big Bang, and right up until then, the universe was like this opaque, soupy plasma. And you said there was too much energy and nothing could really form except for like hydrogen and helium.
Exactly,
and a little bit of lithium. And it was like 5,000 degrees Celsius and stuff like that. And then that amazing transition happened where it was like a flick of a switch in relative terms, and the universe became transparent. When those larger elements and when radiation stopped dominating in the universe and when matter started dominating. It's really cool. And that's why that cosmic microwave background is at that time. That's how far we can see into the past, is 400,000 years, and we have to use other techniques of physics to look further, that which people are literally doing right now. But as it stands, that's kind of our best, we're 400,000 years off.
When you're looking into the night sky and you're looking into the universe, you're looking back in time, because that's the nature of light. If you're looking at a star, the closest star to the Earth is Alpha Centauri, and you're seeing that 4 years ago. when we look far enough back, visually, we can only see as far until everything calms down. Because if we try to look back and see that moment before matter is forming, it's just blinding light. It's just...
Exactly.
It's chaos.
Isn't that incredible? So the universe was an incredibly violent place for at least the first 400,000 years. And then, boom, darkness.
Literally settle, calm, balance. And all of this matter had to come together, and the passive force of gravity pulling particles together. And when there was enough mass in this gas, if it rhymes, if it rhymes, it's true. That's the rule. It will ignite under the pressure of itself and ignite a star. And that was how the first cosmic elements of the universe came to be. The few of our cosmic elements, what we recognize.
Heavier elements.
Then those stars would form, and they would pull in more gases, and then those gases would turn into stars. And you found that you'd have multiple centers. And that's what formed all of these galaxies. You'd have a star form. Let's say you'd have 4 or 5 stars form, a great distance apart from each other. They would pull all of the local gases towards each other, and then those gases would become too compact and they would fuse. And some of those stars are still living, like the small red dwarf stars are still alive from that initial stage, which I think is nuts.
That is amazing. Oh
just
my
like,
God.
Just old man stars going, you haven't seen shit, son.
It's so red. It's just like, I'm so far away from everything.
Yeah. All my friends have died. They've moved on, put on a big old show about it.
A proper veteran, like. Wow.
The very, very big stars turn into supernovae and produce so many things that can actually produce other stars, right? But your smaller stars, they don't explode. They just compact into neutron stars.
They keep going.
They burn their fuel efficiently,
The big stars, they kind of burn big, burn bright, burn young.
Yeah.
Live fast, die young, that sort of stuff.
Damn right. Living it like it's the 60s and 70s,
One thing maybe that we should also talk about in that stage is this amazing stuff that we really don't know much about called dark matter.
Yeah.
I mean, just to put this on a platter, our matter, the stuff we're made of, is only about 5% of the stuff of the universe that is energy or mass. The rest of that stuff is either dark matter or dark energy. And I'll talk a bit about dark energy soon, but that dark matter is basically called that because we just literally have no bloody idea what it is.
It's confusing.
The only reason they know it exists is because cosmologists have looked out at distant galaxies and they see how, for instance, you have a spiral galaxy, and it's you have a huge spiral galaxy, and there's legs on it, and they're kind of rotated, and it all rotates together. But because of gravity, you would expect that the middle of the galaxy would have the most gravitational pull.
Yeah.
And therefore, the legs would kind of trail. That's what you would expect. But researchers in the 80s kind of figured out, they were like, the legs are rotating just as fast around as the center is. They're like, what the hell is giving them that extra gravity on the legs?
Yeah.
And so they just termed it this dark matter. This fills up, 30% of all the matter in the universe. And this is what they think is what gave the universe its kind of microstructure. If you think of it from the grandest scale, the dark matter kind of forms these filaments across large areas, and it coalesces everything. And then there you go. That's why things started coming together. Otherwise, without it, you would imagine that the universe would just be a bunch of hydrogen and helium gas in a big ball.
Perfectly separated from each other, pulled equally in all directions. Yeah, It's kind of scary, though, that 95% of the universe is made up of stuff that we don't understand.
I was researching for this, just simply freaking out. Sure, you know, texting you days before, freaking out, like just absolutely
1
taking
second
it in.
voice messages going,
What is this? This is amazing. The superstructures of the universe have formed, and we're in right now what is known as the stelliferous era, the age of stars and structures. And so the kind of coolest thing is that researchers have figured out that the universe is actually, not only is it growing, it's been growing and expanding ever since the Big Bang. But remember when I said that it went really fast and then it kind of calmed down a bit, and now it's just been going at this constant rate? Well, actually, the expansion of the universe has started accelerating.
It's gaining speed.
The distance between everything is increasing, and I'll explain how that works, because we talked about our matter and we talked about dark matter, but we didn't talk about the 70% of the stuff that makes up the universe, which researchers have termed dark energy.
Oh yeah.
Okay, but before I get into dark energy, let's kind of explain how researchers know that things are moving away from us. When you think about a topic known as the Doppler effect... Andrew, this is for the audience, not for you. I was like, give me a golden star.
Yeah, did I get the gold medal, sir?
That's perfect, Andrew. You do get a golden star.
Yay!
So that's in terms of sound, okay? So when the ambulance goes away, it kind of stretches the sound, okay?
Yeah.
And actually, if you were to plot that, and you were to like put like a color spectrum on it, when it gets stretched, it becomes more red from blue, okay?
Okay.
And the exact same thing happens with light. When you stretch light, it moves from blue, which is a shallow, what we call a wavelength. And when you stretch it, it becomes more and more red. Okay?
Yeah.
And it's not that it turns from physically blue to red light. It's just that it becomes more red.
Yeah.
And so you call this a redshift. So you're talking about the early 20th century. Lemaitre is already figuring out that every single galaxy that he looks at is moving away, or at least most of them. And so that's only been built upon. Researchers have looked at other things like standard candles. And they're a thing where there's what's called a white dwarf star, which is a tiny star, and it's kind of like at the end of its life. And it's actually when a white dwarf is orbiting another larger star, that it actually starts eating that star, and it forms this incredible looking thing on your picture, on your telescope, right? So researchers looked at these standard candles and they looked at the distance, and they know that these standard candles, given the distance away, they should give off a certain amount of light. So therefore they can actually find the distance based on just looking at the luminosity, how much light they're giving off, okay?
Yeah.
That light came to Earth dimmer than it was supposed to. So that means that they're further away than they're supposed to be. So researchers are like, uh-oh. And so two massive research teams did this on the same standard candle, and they found out the same results.
That's so crazy.
And so this is just one example, but there's lots of stuff in the field of cosmology of people just staring out at space and measuring the movement and interaction of stars and galaxies and nebulae, and everything is moving away from us. The theory is that the galaxies aren't actually doing the moving away from us. They are relative to themselves. They are actually stationary. It's actually the space in between us and them that is expanding because of this stuff that I called dark energy.
Yeah.
And so the expansion rate is actually very, very small at small scales and super large at large scales.
Oh, my brain.
The only way I can explain this easily is, so the closest galaxy to us, Andromeda, is actually coming towards us.
Wow.
Our galaxy, the Milky Way, is gravitationally going towards Andromeda. They are going to collide. Okay?
Yeah.
In, I don't know, is it 500 million years or a billion years? That kind of goes against this idea, doesn't it?
Yeah.
Because I thought that every single galaxy is going away from us. But this one isn't. because at small scales, on the grand universal scale, this is small. Gravity wins.
Yeah,
But
okay.
our distance to the next galaxy, dark energy, and this expanding universe wins. And so at these larger scales, things are being stretched a lot more. And it's amazing because they've actually estimated the exact rate of expansion of these pockets of space.
That's crazy.
And so it's estimated to be 74 kilometers per second faster for every 3.3 million light years farther away a galaxy gets from us. Okay? What that means is that a galaxy that's 3.3 million light years away is going away at us from that standard speed, 74, right? Let's say it's just 74.
Yeah.
A galaxy that's twice the distance away is going away at twice the speed. And then 3 times as far away, 3 times the speed.
Okay, I need a drink.
Honestly, though, it is a little bit disheartening, isn't it? It's a little bit scary. I remember when I was I guess I would have been in Leaving Cert in secondary school in Ireland, and they would have been talking about this expanding universe, and I'm pretty sure it scared the shit out of me.
Yeah.
But it is so fascinating at the same time. But it is more so probably scary.
You think all this stuff of like traveling to like distant planets and all of that, and it's like, by the time we make a technology to travel to distant galaxies, will there be any galaxies even close enough to us to get to?
The quick answer is yes, though, because of this amazing thing that this, I guess you could call us lucky, because all of the gravity in our Milky Way galaxy, we're fine. Oh, we're happy as Larry. We're lucky to be in a galaxy like the one we're in. But like if you were like a rogue small cluster of stars, maybe you're fecked.
We could travel to different planets and we could travel to different stars. What I'm saying is the galaxy to galaxy travel, you know, like that type 3 civilization kind of travel where we own the Milky Way galaxy. It's more so the next level, because then we're playing a race of who can travel quicker, us or the ever accelerating expansion of all the space in the universe. And to be honest, I do not back us. That's
I don't
it's a hell
either.
of a thing.
If you think about it like this, there is what is known as our observable universe, right? And that is actually going to get smaller over time because of galaxies that are past that threshold where it's actually faster than the speed of light. It's expanding, and it will encroach on us slowly over time, billions and billions and billions of years. But actually, the amazing thing is we know that based on the Big Bang Theory, the universe is 13.8 billion years old. But astronomers can feckin' look up at the sky. You can look back and see galaxies that are 45 billion light years away.
What?
Explain that to me.
No, Aidan, can you please explain that to me? So, the universe was born 13.8 billion years ago, but we can see galaxies over 40, but there hasn't even been 45 billion light years for it to travel.
And here's the thing, and this is a really important thing for everyone to understand, is that the universe isn't really a sphere. We're not at the center of anything. Anywhere you are in the universe, everything is moving away at this rate, or at least that's what we think. And so the reason that those distant galaxies are 45 billion light years away is because the space in between us and them has expanded faster than the speed of light. So that right at the edge, that stuff is moving very far away relative to us. That's a very important thing, relative to us.
Nuts.
I think the most scary thing, and maybe for astronomers as well, is that observable universe is getting smaller because more and more stuff is getting pushed away from us past that threshold of the speed of light. Once that threshold passes a galaxy where its light is no longer going as fast as the space between us and them, we can't see it anymore, and it's dark.
Yeah. So
it's crazy, isn't it?
And that's a future prospect.
That's what our future is based on these theories, and it really brings us to what the universe will be like at its end. You know what I mean?
We've just laid out the scary, honest truth that everything is literally running away from you like you're a toxic boyfriend. or a toxic girlfriend, that you are being abandoned, you are being left on scene, everything is getting out of dodge by the grandest power of dark energy in the universe.
You just smell. It's your breath.
But like, the universe is expanding faster than the speed of light, so there is a future where you look up at the night sky, or humans, if we don't kill ourselves in the meantime, would look up at the night sky and see nothing, because the light from other things cannot get to us because space is moving apart too quickly. And that's whack. So there's a few different ideas about how the universe may end, right? There's three core ideas. The first idea is following this train of thought, and this is the big chill, or the heat death of the universe. This is when the entire universe continues to expand. Everything expands. Everything goes cold. All of the stars die and burst or decimate, and entropy takes hold. And entropy is basically the rule of what is complicated will simplify. If you have a star that's complicated, it will burn. It will simplify back into smaller, simpler things. And the idea of the big chill is that the universe will keep expanding forever. All of the stars will burn out and die. They'll either become like neutron stars, use their energy and dissipate over trillions of years, or they'll become black holes. And the black holes will absorb everything around them, and over trillions of years, as Stephen Hawking was the one who proved it, they too will vanish. They'll disintegrate. So that was that was the major thing that Stephen Hawking brought into cosmology, right? What he brought in, he had a lot of things around time, right? But one of his most significant productions in science was he proved that where we used to think that black holes would absorb everything into their singularity, absorb all mass and all elements, that they emitted radiation. And over trillions of years, this isn't over a couple billion years, this is trillions, they will emit radiation until they run out of mass and dissipate. The timeline for this is anywhere between 1 trillion years and infinite, because they don't know. Yeah. The big chill is just all the energy is used up and nothing happens. And in order for that to happen, dark energy wins, right? So if dark energy is expanding the universe, it needs to win. The next one is, what if dark energy accelerates too fast and the fundamental aspects of the universe breaks down? So if it goes too quickly and everything just can't handle it, it's already threatening to travel faster than the speed of light. It's expanding unimaginably quick. And this theory is called the Big Tear. The Big Tear, where what it does is space at the moment over the largest scale is expanding. What if it got so quick that it significantly impacted the smallest scale? What if it got so quick that it impacted the space between an atomic nucleus and an orbiting electron? What this theory is that this could happen at any point in the universe, this dark energy expansion event. And if it impacted one piece of an atom and changed the rules of the game for that quantum atom, basically, let's say it added 10% distance that had to be maintained between a center of an atom and an orbiting electron, that changes everything. And that the whole universe from that point, that will spread at the speed of light throughout the whole universe. And it will change all of the rules. Your gravity rule will become messed up because it'll change. It won't exist anymore. Something else will exist. The electromagnetic force that only exists under these important rules and measurements that we have. Everything will change. And the reason it's called the Big Tear is because this will literally shred the universe as we know it. It could no longer exist. And we have no idea. Could happen tomorrow. Probably not. Or it could happen 1 trillion years from now.
A big point of this whole thing is is that important phase transition saying. Like in that last episode where we talked about particle and quantum physics, we talk about there was potentially a phase transition for what is known as the Higgs field, or the God particle, that allows the matter that we are made of to have this amount of mass, a perfect amount of mass for us, right? But it's totally plausible that there could be a point in time where either that Higgs field just pops out of phase, and the whole meaning of our universe stops making sense. But the amazing thing though is that in some of these ideas where that big rip happens, at that lowest level there's the potential that it could actually become a rebirth, but it could become a rebirth and a new big bang with a different set of laws of physics.
Maybe this new universe that could be created could alter dark energy or alter dark matter in such a way that it reversed the impacts. Maybe things could, who knows what could happen. In this new universe, maybe entropy could be reversed. All of the natural laws of hell, even gravity could be reversed. Things will be just like, hell no. You know, there'll be no attraction of masses. Like that's the whole, every concept that we have would vanish and it would be replaced.
That's the interesting thing, because that dark energy is almost the opposite of gravity. It has a repulsive force, right?
Dark energy doesn't have an impact on anything in the universe. It just expands the universe. It doesn't interact with the things in the universe. The universe follows the mass in the universe follows its own rules, its own legislation. It's in its own line at the airport going in for, whether you have a visa or not. It's in its own thing. Dark energy is all out on its own, just messing with sheer space-time, or just space, actually. But the thing is, Aidan, that's not the last theory of how the universe might end. And there's one more. And this theory is called the Big Crunch. The Big Crunch. And what this is what if dark energy runs out? If it hits its top speed? At that point, there is the possibility that gravity could win. What if gravity, such as that between our galaxy and the Andromeda galaxy, wins out and pulls each other together, and then we become a great gravitational force which beats the nearest galaxy's expansion rate? Think of it like running up the escalator going down. The escalator is the dark energy trying to push you down and spread space-time, but if your gravity is strong enough, you can run up it. You're beating the opposing force. So there is the possibility that this gravitational force, if you have more mass and enough mass comes together, it will be stronger. And that's the Big Crunch theory. It's the what if the elastic band of gravity holding all masses connected wins out in the end and pulls it all together. Because the thing with that is that it's saying that everything may compress. All these maybe black holes could compress and form one final singularity. Or dare I say, come together, the whole thing over again, forming a cosmic egg.
A new cosmic egg. And you're just like, is it the cosmic chicken or is it the cosmic egg?
Well, we have three theories. I don't know which one's right.
So is it that in the Big Crunch theory that dark energy becomes weaker or gravity becomes stronger? Which one is it?
It's that it stops accelerating.
It just finishes. It's done. It's done.
Like we've been saying, it dissipates. It cannot maintain the energy it's putting out.
So the tensile strength of an elastic band, you can stretch it for so long and then it'll snap, right? Is just the tensile strength of dark energy. It's this incredibly grand scale, but after 1 trillion years, dark energy snaps.
But the thing is, we don't have a clue what that is. There's no way to know whether dark energy is. It's like a gas tank that will run out, or if it's an infinitesimal guarantee. You don't know that. You can't know that.
Like at the end of anything, we're definitely not surviving. We can say that
whatever
much.
creatures live
But-
that long will not be human. That's just the truth of it.
But there's kind of like this optimistic, at least one or two of those scenarios, there is the chance that things can start again and there's another type of universe with
Yeah.
another set of
You say that,
laws.
but do you really have a deep lying care for if a second universe forms after your mere 60 to 90 year lifetime?
I don't know. For some reason, it would give me a semblance of
It
hope.
would give you a feeling of purpose, of knowing that my work now will not only help my kids, but my kids' kids, and their kids too, and their kids to the power of 45.
and my post Big Bang 2 kids.
Exactly. It's like things like that have.
You leave a little message in quantum fields.
Exactly,
like
yeah.
you're just like, I hope your birthday was good, grandson. From Big Bang 2.
Like, it has absolutely no impact on us. It won't. It's not even like, it's one of those things that, like, it's a curiosity. But my gosh, we have bigger problems. I'm much more concerned about my direct debit paying for my
Definitely.
bills going through than I am about the potential crunch, cooling, or slashing open of the universe in 1 trillion years. Because
Yeah, or people listening to this podcast.
I fear the people listening to this podcast, because if they don't like, subscribe, or follow, we're dust.
And like that, we're gonna big rip out of here. Thank you so much, everyone. Like,
Yeah.
honestly, we loved the first season, and we are gonna keep going. We absolutely love it.
Everything about this is only possible because of you. Thank you so much.